showing that root 2 was irrational, okay? Unless we lied to each other and it wasn't really rational, okay? But it is, okay? So we can say this is a contradiction since we showed root 2 to be irrational. We already proved that. Okay? And Andre, I think that's what you were talking about before. Can we borrow from something that we've already proven? And we certainly just proved that root 2 is irrational. Okay? So we start to have like this bank of things that we know are to be true. Okay? All right. So clearly, that means that the negation is false. The original statement must be true, meaning that this structure, 7 minus 3 roots of 2, is indeed irrational. Okay, I'll finish that up over here.
Realistically, when we're first starting the problem, I mean, if you just kind of do the math in your head, you know it's going to be irrational.
Yep.
So, is that sort of a good way to self-check by solving the problem first?
Oh yeah,
just
absolutely.
mathematically before you actually start?
You always want to see like which one's going to be valid, either the original or the negation. Because remember, only one of them's true. Okay? You can't have the original and the negation both be true. Okay? So I think it's a great idea. Like just in your head say, okay, well if I have to use contradiction, which one of these is true? And if the negation's false, prove it false. Okay? And when I say prove it, like you just keep beating it up with algebra until you get to somewhere where there's a contradiction somewhere. Alright, so thus the negation is false, and the original is true. And we be done. Alright. I think for homework I asked you guys to prove something like 3 plus 5 roots of 3 is irrational. And you can use the fact that root 3 is irrational when you guys prove it, okay? Or if you don't prove it, you can just assume that you proved it, or got it really close to doing it. Okay. All right, guys. So, any questions I can answer about proofs that contain irrational numbers? Okay? Anytime you have irrational numbers, all you guys do is just use contradiction. Okay? It's the easiest way to go about it, okay? All right. So the good news is, for the rest of today, we're done with proofs. Okay, I'm sure you guys have been done with proofs for about, yeah, I know, good stuff. The bad news is on Wednesday we're going to come back to it. Okay, so I know. It's horrible that a math class would contain proofs in it, right?
Why not just switch them around so we finish those first?
Because unfortunately, to do induction, we need to know sequences and we need to know series. Okay, so it's basically like you can't do calculus 1 until you know how to factor a polynomial and basic algebraic operations. So guys, what we're going to do is we're going to start with just some basic sequence stuff, implicit, explicit forms, okay? But a sequence is just a list of elements with some pattern, okay? It doesn't have to be numerical, but for us, we've probably utilized like some sort of numerical sequences. Most of us are probably accustomed to arithmetic sequences. Arithmetic just means you keep adding a number to get there, but that's not the only type of sequence. There's geometric sequences, there's all kinds of sequences that we can try to look at, okay? In this class, we're going to stick to the two most basic ones, arithmetic and geometric, okay? There's first of all something called an implicit form and an explicit form, okay? And then there's a domain and an initial value. So every time you guys have a sequence, there should be four things that are going on, okay? Whenever we talk about the implicit form, okay, so the explicit sequence is just basically like where you can just plug in a number and then you get a number out there, okay? It's almost like the functional form. So if you guys see the word explicit, you can replace that with function. And you guys know what function is, one input, one output sort of thing, okay? The implicit form is where you list out the elements. Okay, so that's sort of like your set builder or your roster notation where you just list out the elements. So implicit is just the long form, it's not as useful. Explicit is the more useful form. And by the way, guys, every sequence has an infinite number of explicit forms. Okay, I want you to notice like this implicit sequence right here, 1, 3, 5, 7, 9. Those are all the odd numbers, right, guys, that are whole. And we know the definition of odd is 2n plus 1. So one way that I could define an odd number if it was a positive, is that a sub n is equal to 2n plus 1, where n starts at 0. Because I plug in 0, I plug in 1, I plug in 2. Or, couldn't I start at 2n minus 1, but start at 1? Because if I plug in 1 here, the output for that is 1. If I plug in 2, that output is 3, right? What if I said the sequence a sub n is equal to 2n minus 5, okay? Couldn't I get that sequence, that explicit form, to give me that implicit form, if n started at what number? 3, right guys? Because think about if you plug in 3. 2 times 3 is 6, 6 minus 5 is 1. Think if you plug in 4, 2 times 4 is going to be 8, 8 minus 5 is 3. So like I said, there are an infinite number of explicit forms that we could do for any sequence if you wanted to. Okay? So, now our job is, if I give you the implicit form, okay, I want you guys to be able to write the explicit form of that sequence. Okay? Some of them are really easy, some of them take a little bit of brain power to be able to work with. Okay? So let's go ahead and try to work with these. Alright, so I want to write, instead of the, it should be an explicit form. So we can just change that to an explicit form, because there are a number of these, okay? Now please be nice to me while you guys are doing this. I know you guys can get really creative, okay? And instead of doing something like really simple, you can make it really complex, and then I have to sit there, and so try to be nice to me as you guys could, okay? But I just want to write an explicit formula for each of the following for each of the sequences. They're not alternating, so we can just cross out the word alternating for right now. Most of them are, but not. So let's start off with one that's really easy.
Now,
Okay?
is n starting at 1 over here?
Well, it doesn't have to. We define the domain.
Okay.
Okay? So it doesn't have to start at 1. And that's why I said there's an infinite number of implicit forms.
Okay.
Okay? So I have 1/2, 1/3, 1/4, 1/5, 1/6. So if I was to ask you guys to write an implicit form for this, okay? Can somebody tell me one implicit form for this, or one explicit form for that sequence?
1 over 1, n plus 1.
Okay, so we have 1 over n plus 1. But, or if we say that, where does n have to start?
1.
Okay, so that means that n is an integer, n bigger than or equal to 1. Okay? And think about that, guys. If you plug in the integers 1, 2, 3, 4, 5, 6, if you plug in 1, that gives you 1/2. If you plug in 2, that gives you 1/3. If you plug in 3, that gives you 1/4. So that implicit form, or explicit form, certainly satisfies that implicit form. Does that make sense, guys? Not difficult. What's another one that you guys could think of? There's certainly more. Go ahead, gentlemen. It doesn't matter who wants to. Okay, so you can do a sub n is equal to 1 over n, where n is an integer, but n is bigger than or equal to 2. Okay, John, were you going to suggest a different, or say one? Okay, he stole it from your mind. It's kind of creepy. Right. Guys, there's an infinite number of those. Okay, it's whatever one you want to start with. Okay. Now, generally, the more simplistic that you can keep the sequence in terms of structure, the easier it's going to be to work with. Okay, so I always suggest, guys, that if you guys can write a more simplistic relation, it's probably better than a. Okay. Now, letter B is a little bit sneakier. Okay. Because notice that the signs are changing. Okay, and that's called an alternating type of sequence. Okay, some of you guys know that, some of you guys don't. But when the signs change, either negative, positive, positive, negative, and if there's like a one-to-one relationship between the parity, that's alternating. Okay, for those of you guys that have suffered through Calc 2 and sequences and series, you know that. If not, don't worry about it. Okay, what I always tell people is ignore the signs, and at the end of the problem, worry about the signs. So, if I was to just ask you guys to write an implicit form, or an explicit sequence for 5, 7, 9, 11, 13, there's a number of ways that we could do this, okay? So, does somebody think they can tell me one explicit sequence for that? So,
N plus 2.
okay, so we could say n plus 2, providing n starts where?
1.
No, 5.
Nope. 3.
3.
Okay, so that's okay. So in fact, I don't think that would work. Because if we plugged in 3, 3 plus 2 would be 5. But what happens when we plug in 4? 4 plus 2 is 6, right? And 6 isn't going to be in this. So you're close, okay?
Yeah, yeah.
Okay, there we go. So 2n plus 1 maybe?
Yeah, let me go.
Yeah, or 2n plus 3, or 2n plus 5, or 2n plus 99, right? It doesn't really matter, because we can do whatever we want. But where should n start if we do this, guys? 2, right? Because 2 times 2 plus 1 is 5. So, now hold on 1 second. Let me rewrite this because I'm going to need a little bit of space here. So we're going to say 2n plus 1, where n is an integer, n is bigger than or equal to 2. And guys, all you do is you just go back to check, and you plug in 2, you plug in 3, you plug in 4, and they should match up to those values, okay? Which they do, right? Except for the parity of odd and even, or for negative and positive. All right. Now, what we need to do is because it's alternating, we need to throw in an alternating factor. So, does anybody remember like that factor that can help you
Negative.
toggle between positive and negative?
Neg-
It was negative 1 to n plus 1.
Right, it could be either be negative 1 to the n or negative 1 to the n plus 1, right? So it's got to be one of the two, all right? Now, John, you used n plus 1, right?
Yes.
Because, well, guys, let's think about how that changes. Okay? What happens if you plug in 2? Oh, by the way, this should be in parentheses as well. Sorry about that. What happens if you plug in 2 into negative 1 to the n plus 1? Does it become negative 1 to the third? And guys, what do you know about negative 1 to the third?
Negative.
It's negative. What happens if you plug in 3? It becomes negative 1 to the fourth, right? Which is positive. And then it goes to 5, which is negative, and then to 6 to positive. So it has that alternating parity, okay? Quite honestly, we could have used n plus 1, n plus 3, n plus 99, whatever we wanted, right, guys? As long as it stays odd and even, that parity between the two, okay? So, and the reason that we wanted to use this one is because we wanted the first term to be negative, right, guys? So if the first term we wanted to be negative, we wanted to make sure that when we plugged in this number, the initial value, it makes that first exponent odd, okay? Because remember, odd, even is going to change the parity, okay? Does that make sense to everybody as to why the negative 1 to the n plus 1 works? If you don't believe me, just make a table of values, and you'll see how it alternates between positives and negatives. All right. Now, what about letter C? Letter C is the exact same problem, except now the first term is positive and the second term is negative.
So you just use negative 1 to the power n. That's it.
Sure, right? You
That's
can
it.
just use negative 1 to the nth power, okay? It's either going to be negative 1 to the n plus 1 or negative 1 to the n. Those are the only two that you should ever consider, okay? So you don't want to consider n plus 33 or 2n plus 55 or anything like that. It's either n plus 1 or n, okay? There's no other way to do it. And what you do is you plug in your number. If that one doesn't work, you use the other one, okay? So that's the easiest way to do it. It's got to be this one or this one. Those are the only two alternating factors that you guys should ever consider, okay? There are a couple other alternating factors, but you probably don't use them for anything. Okay, so let me finish this off. Like, just for fun, I don't know if you guys know this, but cos of n pi is an alternating factor as well. Because depending upon if n is even or odd, if you have cosine of pi, that's negative 1. If you have cosine of 2 pi, that's positive 1. So that's another alternating factor, okay? So you can actually write alternating sequences using trigonometrics, okay? So I don't know how many people ever do that, or if you were in Calc 2, if you ever saw that or not, or if you will see it. But I'm just letting you guys know, if you're ever in a math class and you see something like that, that's another alternating factor. And sometimes it's a sneaky one, okay? Sometimes if you want to go like negative 0, positive 0, negative 0, positive 0, I've seen this one on occasion. You guys don't have to write this down, by the way. I've seen this one. So where what happens is it starts out as, if you plug in 0, it goes to 0, and then 1, and then 0, and then negative 1. So that's another alternating factor, but maybe you only want some of the, every other term to exist. Like maybe if you had an odd function, you only wanted the odd terms to exist, okay? I don't know if you guys remember, but there is a way, like when you guys have heard the terms even and odd refers to its series expansion, okay? Because you can write functions as series sometimes. Is it an odd series? Is it an even series? So, like when you guys were pre-calc, even just means it's symmetric about y, odd means it's symmetric about the origin, okay? And you guys didn't know why it was called even and odd, okay? So, if anybody wants me to keep talking about it, I will, but I guess you guys just want me to get done. Sorry, I get all happy about that stuff. Sorry about that. All right, letter D is probably the sneakiest one, isn't it, guys? Because it starts with a negative, and then all of a sudden, the rest of the terms are positive, okay? So this one's really, really sneaky. So let's call this D sub n. Now this one's not alternating, so we don't need the -1 to anything. Okay? See if there's a relationship between the numbers. Now these aren't arithmetic, right? Guys, arithmetic means you can just add a constant and get to the next number. Okay? And we don't want to use recursion. We don't want to use the fact that you could just say, oh, okay, well the first time I added 3, and then I added 5, and then I added 7, and then I added 9, and then I added 11, etc. Okay? Because that's a recursive sequence. Okay? So we don't want to do that. So does anybody see like a pattern that's going on with those numbers or anything?
Square minus 2.
All of these numbers are 2 less than a perfect square, aren't they? Like for instance, 23 is 25 minus 2. 34 is 36 minus 2. 47 is 49 minus 2. Okay, nice spot. Okay. Even -1. Okay? Guys, what minus 2 is -1? 1, right? Which is a perfect square. So I think John. Oh no, it's not wrong.
No,
It's
I
right.
mean,
He's absolutely
It's
right.
wrong to put that kind of.
Oh,
thing
but
up
that's
there.
why we're doing it together. It is sneaky, isn't it? All right. So D sub n. Mr. Duff, would you be offended if I wrote that as n squared minus 2, 2 less than a perfect square? All right. Now, of course, that's not complete just like it is, right? Because we need an initial value and we need a domain. So the initial value, and I'm guessing this is the one you would think of, John, would probably be n bigger than or equal to 1 to be able to start that. Okay, nice spot. All right. Yeah, that's a little bit difficult to see, okay? And that's why we do it together. So, because we're thinking, okay, well, what can I add to get to the next